yeah, by the way, he worked out all the technical details of the work. And let's start. There is no outline. Since many years ago, I stopped having outline for my talks because I don't think it makes much sense. Nobody's going to memorize the outline anyways, so just follow me. So I'm not sure about the background of or the audience. So let me just briefly introduce what are topological orders or what are topological order metaphysics first. So the discovery or the invention of this notion of topological orders came with the discovery of fractional quantum Hall states in early 1980s. So the interesting thing physicists realized about fractional quantum Hall states is that they seem to be beyond the description of the traditional Landau-Ginzburg symmetry paradigm, a symmetry breaking paradigm classifying phases of matter and their phase transitions. In particular, in the usual Landau-Ginzburg symmetry breaking paradigm, where you have a phase transition between distinct phases of matter, usually there is a symmetry breaking or symmetry restoration. So, however, for the fractional quantum Hall states, the phase transitions between distinct fractional quantum Hall states didn't come with symmetry breaking or restorations because they all share their same symmetry. And then later, some physicists realized that what's most important in characterizing these fractional quantum Hall states are in fact their topological properties. So in phase transition between two distinct fractional quantum Hall states, there is a transition or change, modification of the corresponding topological properties of the fractional quantum Hall states involved in the phase transitions. So then the term this kind of phases of matter, topological phases of matter, and the order in these phases of matter are christened topological orders. And here are some pioneers in this line of research: Professor Yidun Wan at MIT, Tony Z at UCSB, Professor Yongshu Wu at Utah, and Frank Locek at MIT as well. And what are topological orders truly? So today I'm going to focus in 2+1 dimensions. So the 2D here means spatial dimension. And the notion of topological orders can be generalized to arbitrary higher dimensions. But what I'm going to focus on today is two-dimensional cases or 2+1 dimensional cases. Okay, so what are topological orders in 2 dimensions or +1 dimensions? First of all, a topological order or topological phase of matter is defined at 0 temperature. Okay? So at which all the thermal fluctuations are suppressed, and we only have quantum fluctuations. Okay, and a topologically ordered matter phase is a gapped phase. It's a gapped system in the sense that there is a finite gap or this difference between the ground states and their first excitations in such a phase. And this gap is independent of system size and thermodynamical limits. Okay, so because there is a gap, and we can try to look at the ground states and the excitation separately. Okay, so let's look at the ground states first. The ground states are already very interesting because the ground state Hilbert space may not be one-dimensional. Okay? There can be a ground state degeneracy, in other words. And this ground state degeneracy depends on the topology of the system rather than the microscopic interaction details. Okay, by that I mean, by topology of the system, I mean spatial topology, not the topology people usually talk about in topological insulators, okay, which are the topology in the momentum space or K-space. Here, the topology refers to spatial topology. Or in other words, if you have a piece of material, a 2D material, and you can fabricate into a sphere, a spherical surface, then the ground state degeneracy of a topological phase okay, in this material would have a unique ground state. Or in other words, GSD is 1. And if you can fabricate the material into a torus surface, okay, then the ground state degeneracy turns out to be some finite integer k. And if you are able to fabricate the material into a higher genus surface, the genus number is g, then the ground state degeneracy grows as k to the power of g in certain simple case of scenario. Then in more complicated cases, which involve non-abelian topological order, okay, which are our main focus today, the ground state degeneracy doesn't grow in such a simple fashion. Okay. What's interesting about this ground state degeneracy is that as long as you do not alter the spatial topology of the system, okay, or the material, you wouldn't be able to alter this ground state degeneracy of the topological phase, okay, in which this material is prepared in, okay, by local perturbations. Okay. So you can only alter this ground state degeneracy by draw a hole on the sphere or cut the torus open into a cylindrical surface. Okay. So in other words, this kind of ground state degeneracy is topologically protected. So it is also known as topological degeneracy. And Alex Kitaev proposed this idea of utilizing this topologically protected ground state Hilbert space as a way of encoding information. So if you can write information into this ground state Hilbert space, then the information would be very robust against local perturbations. This sets the topological order or topological phases matter very interesting for applications. Okay, so on top of the ground states, there are also these first elementary excitations. These excitations are known as anyons because they are created particles. They exhibit exotic statistics. Okay, so usually we know that elementary particles are bosons and fermions. Okay, if we exchange a pair of bosons, then the correlation function of the system involving these two bosons wouldn't have any change. Okay. So if we exchange a pair of fermions, on the other hand, then the correlation function would acquire minus sign. Okay. What anyon does is, if you exchange a pair of anyons, okay, in such a system, then the corresponding correlation function or wave function would acquire some more general phase vectors rather than just plus and minus ones. So this is why these kind of created particles are referred to as anyons. Okay, as anyons. In any given particular topological phase, an interesting property is that the number of anyon types, because there can be different types of anyons in a topological phase, the number of anyon types is equal to the ground state degeneracy of the phase on the torus. This can be easily proven by using the language of topological field theory. I won't go through it here today. So just keep in mind that the number of anyon types in a given topological phase is equal to the ground state degeneracy of the phase on the torus, not on sphere, not on any higher genus surfaces, okay, but only on the torus. Okay. So the anyons are also very interesting. They are even more interesting than the ground states because you see, if you exchange a pair of anyons, there can be some arbitrary phase vector. Okay. However, if you have a bunch of anyons, and in the case when these anyons are so-called non-abelian anyons, okay, and examples of which we will see very soon later. Okay, if these are a bunch of non-abelian anyons, they occupy certain subspace of the total Hilbert space of the system. So there is a non-trivial subspace of the Hilbert space. Okay? And then if you move these anyons around each other along the time direction, the road lines of these anyons appear to be braided with each other. Okay, and this braiding has a non-trivial effect on this Hilbert subspace occupied by these bunch of non-abelian anyons. Okay, if you carefully design how these anyons are moved around, and in other words, how the world lines are braided with each other, you can encode any kind of unitary operation in this way of braiding. And this unitary operation acts on the initial state in which these anyons reside, okay, and turn it to be certain final state. Okay, and if you read out by measurement, you read out information in this final state, you can achieve the computational result that you want to achieve by this unitary operation. So this is called topological quantum computation. Okay. You can, in fact, you can realize any kind of unitary operation. Okay. For certain Nonabelian anyon system, you can realize any kind of unitary operations on this Hilbert subspace. Okay, therefore, you can achieve the so-called universal quantum computation. And because the braiding is topological, okay, so this is also referred to as topological quantum computation. And the computational procedure is very robust against errors due to local perturbations, because there are no notions of qubits, no notions of physical qubits in this scheme of quantum computation. But this is not our focus today. Just for information, if you didn't know that before. Okay, so let's continue. And any questions so far regarding this basic stuff? If no questions, let me just continue. Okay, so we all know that bosons can condense, as in the Bose-Einstein condensation. Okay, so and this kind of condensation has very interesting consequences. For example, the Cooper pair condensation can lead to the creation of superconductors, and the Higgs boson condensation can lead to the electroweak breaking in particle physics, and such that the elementary particles can have mass. Okay. What's interesting is that anyons may also condense, as these bosons can do. So this is our topic today. To understand anyon condensation, let's quickly recap what are Higgs mechanisms in superconductors and electroweak theory. In a superconductor, in superconductors, there are these Cooper pairs of electrons, and the electrons are paired with each other, okay, with upper spin and downstream. Okay, they're coupled. They are paired into a SU2 singlet. Okay, so they behave like bosons, but charged bosons, and they can condense. After their condensation, okay, the vacuum of the system becomes a sea or an ocean of these condensed Cooper pairs. Okay, because these are charged bosons, okay, when they condense, they will cause the photons because they have electromagnetic interactions. So their condensation will cause the photons. Photons in this framework is gauge boson. It's a gauge boson. Photons to be gapped, or in other words, become massive. Okay, by eating the Goldstone mode of these condensed pairs. And there can be a phenomenon known as confinement as well in the so-called type 2 superconductors. Okay, so in the type 2 superconductors, because of the, there can be a coexistence of superconducting regions and the normal regions, which are not superconducting, because the surface or the domain wall between these conducting and the normal regions have an energy less than 0. So energetically, the system would favor the creation of these domain walls. So the normal regions and the superconducting regions, they can coexist. Okay, and in the normal regions, there can be vortex lines, okay, such that the magnetic flux can go through the core of the vortex lines. Okay, but in the superconducting regions, magnetic fluxes cannot go through, cannot penetrate. And another physical reason or mathematical reason why this can be this kind of confinement of the magnetic fluxes through the normal regions is due to the non-trivial topology of the moduli space or the vacuum structure in a superconducting system. The vacuum or the modular space turns out to be S1, okay, which is a circle. And along the circle, there can be non-contractible loops, okay, like these vortex, stable vortex lines. So this is the underlying physical mathematical reason that there can be these vortex lines, okay, and energetically is the reason why we can have type 2 superconductors. Okay. If this is not true, then we won't even have this possibility. But we need the energetics to really create a type 2 superconductor. Okay, and the magnetic fluxes are confined in the vortex pores in the quantized manner. And the electroweak theory, we have a Higgs mechanism as well. Okay, so the so-called Higgs boson, it is a boson, but it is not really a scalar. It is in fact a quantum doublet. It has four components, okay, 4 components, which transforms under the so-called SU2L, which is isospin gauge group. Okay. Okay. And what the condensation is that one of the, broadly speaking, it is this Higgs boson acquires a non-zero vacuum expectation value. But in studying this kind of condensation, we usually choose a gauge. Okay. The most handy gauge is the so-called unitary gauge, in which the phi 1, phi 2, phi 3, all these 3 components are set to 0, and only the phi 0 component applies this vacuum expectation value. Okay. So after this Cooper-Pairs after the Higgs boson condensation, okay, the original massless W and B bosons. So you see, originally, this is the gauge coupling between the gauge field. This is the SU2L, isospin gauge field. And this B is the hypercharged gauge field, U1Y. Okay, so there is no electromagnetism at all before Higgs boson condensation. Okay, there's no electricity, no photons at all. There's no notion of photons. Okay, so this is the gauge coupling between these gauge fields and the Higgs boson. Okay, so after the Higgs boson condensation, this guy becomes kind of constant VUV, right? Kind of constant VUV, such that this W and B may acquire mass, and under certain recombination of the degrees of freedom, they become the W. Okay, there is a W plus minus which combines W1 and W2, and Z is the Z boson which combines the third component of W with the B field. Okay, and there's a residual gauge invariance, which is the U1 electromagnetism. Okay, which also combines W3 and B, okay, into the residual gauge field, massless gauge field. So after condensation, the W plus minus and Z, they become massive. The mass is in fact proportional to this VUV of the Higgs boson. Okay, and there's a phenomena which now we understand as splitting. The reason is that before Higgs boson condensation, okay, the left-handed electron and the left-handed electron neutrino, they together is a what? It's a gauge doublet of this SU2L isospin gauge field. Okay. So these two are in fact the gauge degrees freedom. Okay. So they are not truly physical degrees of freedom because they are up to gauge choices. Okay. So originally these two are kind of the same particle into a doublet state of the W field. However, after condensation, this W becomes massive. So this ceases to be a gauge coupling between EL and the new EL. So after condensation, new EL and the EL and the new EL becomes two distinct particles. They acquire distinct masses and distinct charges. E will become charged, and the neutrino would remain neutral. So this phenomenon, we call it splitting. Okay. there is also a phenomenon that we now understand as identification. Particle physicists won't try to interpret these phenomena in this way, okay? But I'm going to, I interpret these two phenomena in this way because I want to compare this with anyon condensation, what's happening in anyon condensation. So what's identification? This is before the Higgs boson condensation. The left-handed electron and right-handed electrons, they are coupled through a Yukawa type of coupling term. Okay, by what? By the Higgs boson field. So this is a Yukawa type of coupling. After condensation, in this unitary gauge, this phi naught, phi 3 is set to 0, and phi naught becomes kind of constant VUV. Okay, so these two, this Yukawa term is turned into a master of the electrons. So in other words, the left-handed electron and right-handed electron, they are identified into a Dirac fermion. So this is the master of this Dirac fermion. Okay. So the originally distinct particles, left-handed electron and right-handed electrons, they now become the same particle. So this is what we call identification. In the electroweak breaking, there is no confinement of anything because the modular space or vacuum topology in the electroweak theory is trivial. It is S3. In S3 or three-dimensional sphere, there's no non-contractible loops. Okay, so there won't be any confinement in the electroweak breaking. So any questions regarding this a little bit historical review, the essence of if no questions, I'll just jump into anyon condensation. So let's try to compare anyon condensation at large with the usual Higgs mechanism. Okay, that's the knowledge. Okay, what I'm going to convey here is that the phenomena that we saw in Cooper pair condensation and Higgs boson condensation arise in anyon condensation as well. And then I'm going to study why this is so. Okay. Anyons of certain types are condensed, okay, like the Cooper pairs and Higgs boson. What kind of types of anyons can condense? There are these anyons that, although they are anyons, they behave like bosons. Okay. If you move them around each other, there's no non-trivial phase factors generated. So these condensed anyons, they behave like bosons with one another, with respect to one another. Okay, and the anyon condensation in certain parent topological phase can lead to a child topological phase. And the ground state of the child topological phase is a coherent state of the condensed anyons, similar to the Cooper pair condensation or Higgs boson condensation.
You mean one representative ground state?
We can do it on sphere. There is a unique ground state.
I mean, to have a condensate, I don't demand coherent state.
In this case, the ground states are the coherent state of condensed fluid pairs.
I think the statement is if it is a coherent state, then there is condensation.
Yeah.
But there are also other states which also have condensation.
And maybe here we demand it to be a coherent state of condensed atoms. And now by our construction, it'll turn out to be a coherent state. And there will be splitting as well. Certain anion in after the condensation would split into different sectors. And these sectors, certain these different sectors may be identified, okay, similar to the identification in electroweak breaking. Okay. And there may be confinement as well. Certain sectors will be confined in the child phase. They won't be regarded as elementary excitations in the child topological phase because you would have to conquer a huge energy barrier, okay, to excite them. So they're kind of confined. And similar to the magnetic flux confinement in superconductors, but there's no such a phenomenon in the case of electroweak theory. Okay. And You see, in the usual Higgs mechanism, the original massless gauge fields will become massive, or at least certain components of them will become massive. And it is similar in the case of anyon condensation. Okay, certain gauge fields will become, or certain degrees of freedom of a gauge field will become massive, or in other words, gapped. So how do we study anyon condensation usually? Okay. Usually, we study anyon condensation using an abstract language, tensor category. The parent topological order, whose its topological properties are described by the so-called unitary modular tensor category. So this is a seminar, right? So a seminar is not supposed to make everybody understand. So there will be terminologies and technicalities. So forgive me if you wouldn't be able to follow, but you can always stop me if you have questions. Okay, and this unitary modular tensor category captures all the topological properties of the parent topological order. For example, the anyon types are labeled as or represented as simple objects in this unitary modular tensor category. Okay, and the braiding statistics of these anyons among these anyons are captured by so-called modular S and T matrices of this UMTC. And we can choose certain types of anyons in this parent topological order to condense. And mathematically, this condensate is described by a so-called twist-free commutative. It should be a special Frobenius algebra or just a separable algebra, but we call it CSFA in other cases. It's abbreviated as CSFA. Okay. As a composite object in this UMTC, okay, it is basically, you can understand it as a kind of direct sum of the condensed anyons, which are the simple, certain selected simple objects in this UMTC. Okay, and twist-free means that okay, these are bosons, and commutative means that they are mutually boson. And the condensation will lead to a child topological order. In certain cases, the child topological order are basically triplet. Okay, and this child topological order is described by a so-called representation category of this Frobenius algebra A. Okay, and this not here, okay, means that we have to exclude the confined atoms or confined sectors. Okay, if without this zero, then this representation category of this Frobenius algebra includes both confined and unconfined sectors. With this subscript not here, it refers to the fact that we have to exclude the confined sectors. Okay. And the child vacuum is the trigger representation of this Frobenius algebra. Okay. And the child anyon types are just the simple objects in this representation category. Or in other words, irreducible representations. Okay. Mathematicians prefer to call it modules, but anyway.
Now, I have a question about the replication category. This is the vector space replication category, or the replication category in this model.
Yeah, this is in fact the module category of A over C.
So this is just some category between
yeah, right. Yes. Okay. This abstract framework or language is good enough to acquire all these facts. Okay, all these facts. Okay. However,
in the presence of splitting, why is that a subcategory of the original category?
Sorry?
If there's splitting.
Oh, yeah, because this is a category. A category has infinite number of objects. So in the case of splitting, you can understand it as an object requires multiplicities. Okay, and identity. And these objects are not, in fact, the simple objects in the original category. So by embedding this guy into this guy, it simply says that the embedding morphisms are not so trivial. It's not a from a simple object to a simple object. And this is well understood. So yeah. However, there are cons of this abstract language. Okay. This language can only describe the relationships between the topological properties of the parent and child orders. Okay. But it is not able to truly capture the physical meaning of what does it really truly mean by splitting and identification, for example. You see, in the UMTC language, an anyon is a simple object. Simple object is something one-dimensional. Okay, there's no anything internal. However, if we try to understand topological physics as emerging from certain underlying microscopic systems, so these guys, they must be certain subspaces of the total Hilbert space of the system. So they truly have internal space. Okay, so we need and this language is not able to capture this internal structure of these anyons, which simply treat them as simple objects. Okay, they're one-dimensional. Oh, I should say their whole space is one-dimensional. Okay, there's nothing you can extract out of that. Okay, so we need a language, or in other words, a model, okay, in which we have concrete Hilbert space, and these anyons, each anyon would occupy certain subspace of this total Hilbert space, such that we can study this phenomena truly in details and understand their physics. Okay, so we need a basic field configurations, and we need concrete Hilbert spaces. But not words, we need a model with a Hamiltonian, such that we can study anyon condensation or even dynamic work. They want to take a picture. Okay. So we need a model. Okay, what does it mean? We know that certain types of anyon in a parent topological phase can condense. Now, suppose we have a Hamiltonian of the parent topological phase. Okay. Now we add to the parent Hamiltonian an extra term. Okay, actually, and this may not be a derivation. This lambda goes from 0 to infinity. If lambda is 0, it is the Hamiltonian of the original model or original the parent phase. Okay, and when lambda goes to infinity, what will happen? What will happen depends on what this P is. This P is in fact a projector. We'll see what it does. And first, it'll project the parent Hilbert space into the child Hilbert space. Okay, and the parent Hamiltonian is projected into the child Hamiltonian. Okay, this is an operator, so we have P on both sides. Okay, and the ground state of the child phase is projected from that of the parent phase. Okay. So this projector, in fact, will give us a coherent state of this or of arbitrarily many condensed anyons over the system. So you see, a projector has eigenvalues 1 and 0. So when lambda goes to infinity or large enough, the ground state of the system will be dominated by the +1 eigenstates of this projector. Okay, and if we can construct the +1 eigenstate of this projector as a coherent state of the condensed anyon, then we are done.
So I'm confused. So if lambda is infinity, then the Hamiltonian is simply minus P. Right?
Yeah, it's not. I mean, the ground state is dominated by the +1 eigenstates of P.
Yeah, but so suppose lambda is infinity, then the Hamiltonian is basically just a minus P. Because the parent Hamiltonian itself has a finite energy density. I guess I'm trying to understand.
No. That's not entirely true. This is what I'm going to say. Okay. When I show you this construction. Okay. So just hold on for a moment. Okay, you will see. So the excited states of in the child phase are also projected from those of the parent phase. So we are trying to express the projector as a sum of condensed anyon creation operators. So we need truly a model to achieve it. This is just an idea, okay, an idea of the goal we want to achieve. So what model should we look at? Right? The most general model, or in other words, lattice model of 2+1d topological phases. Okay, but only the so-called non-chiral double phases, or the so-called stringnet model. Okay, it is the most general one. But this model is not able to describe the chiral topological phases, which are beyond our description today. Okay, so we'll take the stringnet model, but not the original version, but our version. Okay, so we'll explain why here. So this is the stringnet model, original setup of the original stringnet model. It is defined on the honeycomb lattice. In fact, the shape of the lattice doesn't really matter, okay, because it is a fixed point Hamiltonian describing the topological phase. So you can choose different lattice configuration. Okay. So because it is a model, lattice Hamiltonian model, it has basic degrees of freedom. The basic degrees of freedom form a so-called unitary fusion category. Okay. So these unitary fusion category you can understand as a set, okay, which consists of a bunch of elements. We call them simple objects. Okay, and they are non-simple objects which can be created by these simple objects. So we don't talk about them here. Okay, and these objects, they can fuse. Okay, two objects can fuse and produce other objects. So this is called fusion. So this is why this kind of set is referred to as a fusion category. Okay, you can regard a group as a fusion category. Okay, the multiplication of two group elements producing another group element is a kind of fusion. Okay, kind of fusion. So these basic degrees of freedom live on the edges of the model. Okay. They behave like gauge fields. Okay. And the Hamiltonian of this original stringnet model consists of two kinds of operators, AV operators and BP operators. And an AV operator acts on a vertex, and BP operator acts on a plaquette. What the AV operator does is to detect whether the fusion rule is satisfied. For example, in the case of a group, if you have two group elements, G1 and G2, they multiply to produce some group element H. But here on this edge, you have G1 and G2 here, but on this edge, you don't have H, you have some H prime. Then you say that the fusion rule is broken. And in the language of gauge theory, you say the Gauss law is violated. Okay, so there should be an existence of a charge excitation here. Okay, charge excitation. So the AV operator simply detects whether the Gauss law is violated. Okay. A BP operator detects whether within this plaquette there is a flux going through. Okay. So the BP detects the existence of flux.
That's a question.
I cannot see. What's the question?
It's a bit known. You can, I think you can see.
No, I think.
Oh, you understand. So the question is about the statement that the number of anyon types in a given topological phase is equal to the ground state degeneracy on torus. And the question is asking specifically about the example of Yidun Wan state. The question is just what are the three types of, for example, what are the three types of anyons in the Yidun Wan state? Moiety is not right. So I think the answer to this question is simply there's indeed only one anyon carrying charge 1e/3. Then there's another anyon carrying charge 3/3. This is the other anyon. And then the third anyon is the trivial anyon. I hope this clarifies the question.
Yeah, I think so.
Hmm.
All right. So the Hamiltonian is written as a sum of these two types of operators, sum over all the vertices and all the crosscuts. So this Hamiltonian has this. So this Hamiltonian is exactly solvable. AB and DT, they are all commuting projectors. It is exactly solvable. And the ground states are the common +1 eigenstates of all the AB and DT operators. But this model lacks the ability of describing the full spectrum of this of the corresponding string corresponding topological phase, because this AB operator it is able to detect whether there is a charge, there is a violation of Gauss law or not, or whether there's a charge excitation or not, but it's not able to tell which charge excitation it is. More precisely speaking, in this model, it is one cannot construct the creation operator of a particular charge excitation. So one usually needs to modify this original string-net model, okay, such that it is able to capture the full spectrum of the topological phase it's supposed to describe, okay, and able to write down these creation operators of these anyons. Okay, there are different ways of modifying the string-net model, and the way we adopt here is by transferring any violation of the Gauss law at the vertex to a tail, okay, to a tail extending from somewhere near this vertex into the plaquette. So in this modified setup, all the vertices must satisfy Gauss law. So the Gauss law is now imposed as a dynamical constraint on our system. The Gauss laws are all imposed at the vertices. However, the possible charge excitations are captured by the tails. So the tail also carry degrees of freedom taking value in this original unitary fusion category because they are gauge charges. So after this modification, the Hamiltonian of the model can be written as the sum of only one type of operators, okay, BP, which is the plaquette operator, the original plaquette operator, and the delta function, okay, that simply detects whether the tail carries a trivial degree of freedom or not. Okay, if it is trivial, then this is 1, the delta function is 1, and BP, we can then study BP. Okay, if the tail has a non-trivial value, means that there's a charge excitation, okay, then the entire term vanishes. And okay, with this modified model, we're able to write down the ribbon operators or creation operators, annihilation operators of any kind of annual excitations in the system with internal degrees of freedom.
Okay, so here the plaquette operator has the same certain loop in this plaquette. Here the phase operator does not change.
Yeah,
but there is a new edge in this phase.
Yes, the edge, this tail carries whatever a charge, possible charge degree of freedom.
Yeah.
In the model. So in other words, in this modified model, an annual excitation is placed within a plaquette with possible flux, a possible flux content and a possible charge. So in this language, we can have pure charge. We can have pure fluxes and also diodes. The flux bound with the charge.
Yeah, but why we need to remove this vertex operator? Because
this vertex operator simply detects whether a vertex violates the Gauss law. But now in our modified model, we impose Gauss law everywhere at the vertices. So all the vertices satisfy the fusion rule.
So you mean just the, Hilbert spaces?
Yeah. In this modified model, in the Hilbert, we won't have any violation of fusion rules at the vertices. Okay. And any such violation is transferred into a degree freedom on the tail. So that's the trick we did. So the ground states are all the +1 eigenstates of all the QP property operators. And when QP returns 0 for certain bracket P, okay, it is an excited state. Okay, and an anyon type in this model is a simple object in the Drinfeld center of the input fusion category. Okay, in a packet where this QP returns 0 when it acts on the state. Okay, and we can define creation operators or ribbon operators that creates a pair of anyons J. Okay, a pair of anyons J. Okay, crossing an edge. Okay, in the two neighboring buckets. However, this pair of anyons J may carry different internal charges P and Q. So that's why we have a label P and Q here. This P and Q are degree freedom. The value of the degree freedom are the tails. So this W acts on any state, okay, and creates a pair of anyon with type J, and that with distinct internal charges. Okay. So in this model, all the anyon excitations are represented as diodes in general. It has both the flux and the charge. Okay. In certain cases, the charge is trivial, and then we have pure fluxons. Okay. So this way we can manifest the internal spaces of anyons, non-abelian anyons. Abelian anyons have internal space. Okay. So here is an example. Suppose we consider the input unitary fusion category as the so-called Fibonacci category that has only two objects, 1 and tau. And 1 is the unit object. It is always there for mathematical completeness. And tau is the only non-trivial guy. And the fusion rule is tau fused with tau creates 1 and tau. Okay, so it is a bit more than Z2. And anyon types are simple objects in the Drinfeld center of this Fibonacci category. Okay. It has 4 distinct anyon types. We can label them as 1 bar, 1 tau bar, tau 1 bar, tau bar. Okay. And however, if we are talking about quasi particle excitations, there can be 5 different types. So this tau bar may carry 2 distinct charges. One charge is trivial, and the other charge is non-trivial tau. So this guy can be referred to as pure fluxon because it doesn't have any non-trivial charge. And this is a diol, and this is also a diol. This is another diol type, because it can only carry non-trivial charge. They won't have the corresponding fluxon representation. And this is the trivial particle, trivial anyon or vacuum.
So can the last 2 types of dions be detected by breeding?
Yes. But the total gradient of tau bar itself can be obtained. You see, some of these non-trivial gradient between these 2 guys will be cancelled out to obtain the total the gradient of this anyon tau bar.
Okay. I'll just make the I want to distinguish the last 2 dions.
You cannot distinguish them because these are internal gauge charges. So in other words, when you create a pair of tau bar in the 2 buckets, what you have is a 4-dimensional space. And these are basically 2 basis vectors of the space. Okay. So this is 2 basis vectors of 1 tau bar anyon. But you always create a pair, right? So the total Hilbert the subspace is 4-dimensional. Okay. So you have 4 distinct you can have 4 distinct basis vectors of this space. But this definition or this choice of basis vectors is up to gauge transformation. So these one and how they do have invariant meaning.
Okay.
They don't have invariant meaning unless in certain cases there is a global symmetry that can be imposed on the system such that these gauge charges become global charges, and then they are manifest, and then you are able to measure them. But so far, they're just internal gauge charges, which you cannot truly assign invariant meaning to them. Okay, so we're going to study anyon condensation in string net model. So the Hamiltonian we're going to construct is this. This HF is the Hamiltonian, string net Hamiltonian, or modified string net Hamiltonian of certain parent topological base. And then we add to this guy this condensation term. And I'm going to answer a question soon. So we sum over all the edges. Each of this bunch acts on an edge. Okay. Well, the sum is suppose we're trying to condense not a single type of anyons. We condense multiple type of anyons together. So we have to sum over to condense the anyon types. And then we have to sum over the internal charges because these are not physical degree of freedom. So we have to sum them over, right? Sum of them over. This is the creation operator, okay, that creates a pair of J with charges P and Q, okay, on both ends, on the two ends. And this is some combination coefficients, which are to be determined by requiring that this guy is a projector. It is a local projector. So the sum is not a projector anymore. Each term is a projector. So what this projector does is it projects out certain basic degrees of freedom of the original model or of the parent model. Okay, so in other words, certain, you see, the original input unitary vision category whose simple objects are what? Are the gauge degree freedom. Okay. So this means that certain original parent gauge degree freedom will be projected out. Or in other words, because of this guy, when this guy goes to infinity, they are infinitely gapped. They're infinitely gapped. It's like the W and Z bosons. Okay. Originally, W has 3 components. It's an SU2 gauge field, right? However, after Higgs condensation, Higgs boson condensation, okay, 2 components of the W field combine into W plus minus, which become massive. Okay, and one component is combined with the B field to create a massive and a massless gauge field. Okay, so there will be certain remaining massless gauge degrees of freedom, and there will be also gapped gauge degrees of freedom. And the gapped ones are truly those that are projected out by this local projector that we construct. So you see, when lambda goes to infinity, we have a model not truly. What you said is basically correct. It is dominated. It is essentially this guy. However, this guy only projects out certain degrees of freedom. There are other degrees of freedom that are not really projected out. Those will be combined with this parent Hamiltonian into a child Hamiltonian. So we will have a subcategory of the original input fusion category, in which it has only a subset of the degrees of freedom in the original fusion category F. Okay, and these degrees of freedom are the basic degrees of freedom of the child phase, or the child string net model. Okay. So the question boils down to how to calculate these coefficients such that we can really construct this bunch as a local projector that can realize our goal. Okay.
So do those projectors commute?
No.
They do commute.
This term does not commute with the parent Hamiltonian.
Yeah, I mean, it's within itself, do different terms commute?
It depends. It depends. If it is abelian, it both commute.
So in the regime where lambda is large, if I want to understand this model, I will first only look at the second term and ignore HF. then if the projectors do not commute, is this a frustration-free Hamiltonian?
Yeah. So what we can do so far is only study the case of lambda being 0 and being infinity. Okay. In any finite lambda value, this is not an exactly solvable model. We don't know how to deal with it. We're trying numerical methods. Okay. So when lambda is 0, we got the parent Hamiltonian. Lambda is infinity, we have the child Hamiltonian. And what this term does is simply project out. We know because we can explicitly rewrite this guy as a projector. So what it does is simply project out certain basic degrees of freedom in the parent Hamiltonian. The Hamiltonian always remains the same as the parent Hamiltonian. It is just that to excite certain charges, okay, in the original parent phase, it will conquer an infinite barrier. So those guys will cease to be basic gauge degrees of freedom in the model anymore. So you don't really need to study the details of this because we can rewrite this as a projector. So
I'm not sure this is how the model is solved.
This is the effect of the model. This is what happens when lambda goes to infinity. This guy simply projects out basically the local degrees of freedom. So just you won't see them in your final model.
I mean,
when lambda goes to infinity.
That I understand. Yeah. But I think this is not enough to say that the child Hamiltonian is PHFP.
Why not?
Can you develop it?
Yeah, we can actually derive this.
So to solve the case when lambda is infinity, I need to first look at the second term. I should be able to solve that term first.
Yeah, right. This is what we're going to do now.
Yeah, to solve this question, I don't need to think of HF at all. The property of the second term is purely determined by the second term. Now maybe the second term has many degenerate ground states. And then I want to include the effect of the HF to a 1 over lambda expansion to obtain the effect of Hamiltonian. I think your statement is, indeed, there is a large degenerate ground state space. And then after doing the expansion, the first term is PHFP. But I think this requires quite some technical justification, which is not immediately obvious to me.
We can show you this in our discussion now. Yeah. We can actually show this. So in the case of lambda goes to infinity, the basic degrees of freedom on the edges are projected into a subcategory of the original illusion category. Okay, but keep in mind that this is a subcategory, not a so-called full subcategory. In the case of full subcategory, each simple object in this S is a simple object in the original illusion category. However, in the case of a generic subcategory, a simple object in S may not be a simple object in F. So this is the actual difficulty, okay, that we're going to solve. Okay, so the question is, first, how can we solve this in such that F becomes a projector? Okay. In the case of the so-called Fluxon condensation, things becomes very simple. Okay. In the case of Fluxon condensation, I mean, the condensed anyons do not have any non-trivial charges. Okay. We only condense the pure fluxons. And all fluxons, they commute, in fact. So all fluxons are mutually bosons with respect to each other. So we can condense these fluxons or multiple types of fluxons. Okay. So in the case of Fluxon condensation, it turns out the subcategory that remains, okay, is always a full subcategory of the original input illusion. So in this case, things become very simple. And in fact, in the case of Fluxon condensation has been done by others as well. Okay. For example, I think Fiona did Fluxon condensation as well. Okay. So in the case of Fluxon condensation, we don't really need to start with the Hamiltonian we constructed, we know what the projector would be in the end. So the projector is simply a delta function that projects out certain simple objects in the parent fusion category. So what does C? This is supposed to be S. Okay. It's a typo. So we project out certain such that this is a well-defined. S is well-defined full subcategory. Okay. So fluxons have only trivial charge one. So in this case, any basis state in the Hilbert space, the total Hilbert space, is an eigenstate of this fluxon creation operator for any T. Okay. But with different eigenvalue. So we just need to solve a linear equation. Okay, rather than, you see, we require that P to be a projector. In principle, we need an equation P squared equal P, right? To truly solve those coefficients pi. But in the case of fluxon condensation, things becomes much simpler. The original quadratic equations of matrices become a linear equation. And this linear equation always has equal number of unknowns and equal number of equations.
Just to make sure, do you mean each term is a projector or the sum is a projector?
Sorry?
Do you mean each term is a projector or the entire sum is a projector?
Each term here is a projector. Each term that acts on an edge is a projector. Is P.
So
This is a projector.
the blue box is a projector.
Yeah, yes. But the sum is not a projector.
After the summation is not a projector.
Yeah.
I see.
It's not a projector.
And those projectors do not necessarily commute.
Local projector.
PE for different.
They do not necessarily.
Okay.
Okay. So we can simply solve this set of linear equations and find out all these non-zero coefficients pi, and then we obtain the explicit expression of the projector Okay. Here's an example. We still take Fibonacci as an example. So this is the parent of C. Okay. And we can take a full subcategory, which is the trivial subcategory that has only the trivial object. So what the PE does is project out tau. Okay. So after the projection, the model becomes trivial because there's any non-trivial degree of freedom remaining on the lattice. And this complies with our knowledge that condensing the so-called tau bar anyon leads to a trivial phase. It breaks completely the double Fibonacci topological order. Okay. So here are the fluxons, tau bar 1, and this is the trivial guy. The trivial guy is always included in the condensation because the condensed fluxons will become part of the new vacuum. So it'll be identified with the original vacuum. And then we can compute this eigenvalues W, and then solve this equation, find out this pi coefficients. And then we know that the projector is a combination of W11 bar and W tau bar in this case. Okay. We ignore the trivial charges. So it's a non-trivial combination of these two guys. So you cannot just naively write down an equal probability or equal weight combination of these. It's a particular combination of W11 bar, which is trivial, its identity, and W tau bar. Okay. So this is our actual projector as a combination of the creation operators of the condensed anyons. So you can see that this truly condenses tau bar. And we didn't know this before. Okay, we start with choosing certain four subcategory. And this is what we derived by solving this equation. Okay, we know that what it truly condenses is tau bar, and the fluxon part. However, in the case of dion condensation, this becomes much more involved. Because this is a quadratic, highly degenerate equation of matrices. Okay. So in principle, it's very difficult to solve. Okay. Very difficult to solve. So we won't be able to do things as easy as in the case of fluxon condensation. So we need to figure out a different way. It turns out there is a way. Okay. In fact, for a string net model, okay, there always exists another string net model that is regarded as dual to the original string net model, in the sense that they describe the same topological order. Or the Drinfeld center of the two different, apparently distinct fusion categories are isomorphic or the same. Okay, so we can always find an equivalent parent model. Okay? And we perform fluxon condensation in this equivalent model to obtain a child model. And by a duality map that I'm going to explain soon, okay, back to the original parent model, such that this fluxon condensation turns out to be a non-fluxon or dion condensation in the original parent model, and leads to a child model. Okay, so there is a full cumulative map here, cumulative here. Okay, and this entire cumulative map can be regarded as what's known as mathematically a pseudo-natural transformation. Okay, from this bottom one, this equivalent procedure to the original procedure in which we want to condense diodes. And here we condense only fluxons. And here we just need to select any four subcategory. It corresponds definitely to a fluxon condensation. And by this pseudo-natural transformation that is represented by this duality map, we can go back to the original parent phase in which this fluxon condensation becomes a dion condensation and leads to a child string net model with very highly non-trivial input unitary fusion category.
Question. Here, the child model is not clear. It is also a Finnish model, but this means that the child model also describes the non-terror.
No.
So does this mean that the child model also is always the non-terror phase?
Yes. Here, everything we consider only double phase. We are using string net models, so we can only describe what's happening in double phase. And in parallel phases, we don't know how to deal with that.
So after the condensation phase, it also
yeah, it's all done. Yes, always done. Right. So what do we mean by this strategy? Okay. Suppose we have a topological order in the abstract sense, and its topological properties are describable by a unitary modular tensor category C, and we can have a string net model, okay, whose the Drinfeld center of the input fusion category F of the string net model is in fact the C, or isomorphic to the C. Okay, but we can have another model that has a apparently different input fusion category F prime, which has the same or isomorphic Drinfeld center. Then these two string net models can be regarded as equivalent in the sense, or dual to each other in the sense. And then we can establish a duality map between this equivalent model and the original string net model that we are interested in, okay, to have a construct a dion condensation. And more precisely speaking, when two unitary fusion categories are equivalent or dual in this sense, okay, this is true even only if one of the two unitary fusion categories is a bimodule category of certain Frobenius algebra object in the other unitary fusion category. And this is a theorem proven by Eddington in one of his works in 2015. It's a book. So the theory may be early, but I just took that from the book. Okay. So in mathematical terms, we say that this f and f prime are categorically Morita equivalent. So here we need to understand a few elements from Frobenius algebra, and it's by module category. So what is the Frobenius algebra? The Frobenius algebra is, in fact, a composite object in a unitary fusion category F. Okay, the elements or the basis elements of this algebra, it is algebra, so it is in the first place a vector space. So a vector space has basis elements, right? So the basis elements of this Frobenius algebra are simple objects of this fusion category F. However, it may appear multiple times, so it can have a multiplicity index alpha. This can be easily understood in the case of rep S3. Suppose you take the three irreducible representations of the permutation group S3 as your fusion category, as a fusion category. Then there exists a Frobenius algebra that can be written as 1 plus 1 plus 1 bar plus 2 plus 2. The 2 is the two-dimensional irreducible representation of S3. However, in this Frobenius algebra, it appears twice because this Frobenius algebra corresponds to the regular representation of S3. And we know that in the regular representation of S3, the two-dimensional irreducible representation appears twice, right? It's replicated. So this index alpha is called multiplicity index. Okay. And because it's an algebra, we have algebra multiplication. And it maps three algebra elements into a complex number. And the multiplication must be associated. And this is simply the definition of this algebra. And it has other conditions, which I don't bother writing down here. And here's an example, still about the Fibonacci fusion category. And we can take a Frobenius algebra A as 1 plus tau. So the basis elements are 1 and tau. And these are the multiplication rules of these guys. 1. And there's no multiplicity in this case. We only have 1 and tau. So these are the multiplication rules of these two basis elements. And what about bimodules? Bimodule of the Frobenius algebra is a particular representation of the Frobenius algebra. Okay, so you see, a bimodule is defined as a pair. This is analogous to the definition of a group representation. Okay, we define it as a pair in which we have a row and a representation V, representation space V. Here is similar. We have a Lm and the P. P plays the role of the row of group representation. And this Lm plays the role of the representation space, okay, of a group representation. Okay. It is just that in the case of group representation, the row is a matrix. However, here, because this is the bimodule, the P appears to be a rank 3 tensor with two indices. Okay. How can we understand this? As a representation, it must satisfy the homomorphism condition. This is the homomorphism condition. The bimodule means that the algebra can act on the representation space from both sides. And if you cover, suppose you cover the one half of the side, cover one half of the diagram, this becomes simply the group homomorphism condition of a group representation. Right? It's rho of G times rho of H equal to rho of G times H. Right. So this is just a more complicated but the same kind of homomorphism relation. Okay. And the P has two labels, which are the two algebra elements. Okay. For any given pair of algebra elements, it is a rank 3 tensor. It maps 3 objects into the C number. So this is called a bimodule or bi-representation if you prefer. Okay. So mathematicians would be angry if I call it a representation. So anyway, And here's an example. We still take the Frobenius algebra example we looked at earlier, just 1 and tau. And this Frobenius algebra has exactly two irreducible bimodules, or the so-called simple bimodules. One is trivial. The trivial one is in fact the algebra itself. Okay, algebra itself. And there's a non-trivial. The non-trivial one has three basis elements, in which this tau carries a multiplicity index. Or in other words, this tau appears twice, similar to the two-dimensional irreducible representation of S3 appearing twice in the regular representation of S3. So, and this M1 and M tau together forms a bimodule category of this Frobenius algebra A. Okay. And this bimodule category is in fact isomorphic to the original Fibonacci fusion category. Okay, so now with the equivalent or dual model defined by the bimodule category of this Frobenius algebra A, okay, we can establish a duality map from the dual model, basic degree of freedom of the dual model, into the basic degrees of freedom of the parent model, or the original model. Okay, this is the duality map, and these coefficients are the so-called P tensors. This is the rank 3 tensor. Okay, and a plaquette can also be mapped to a plaquette, a superposition of the plaquettes in the original model. Okay, here, but just keep in mind that after this duality map, gauge charge, the tail, which carries gauge charges, these gauge charges may be enlarged to carry this multiplicity index. So this is the only thing you need to be worried about. The physical reason behind this is, suppose you have a topological order whose properties are describable by this UMTC. Okay, and then because this UMTC can be understood as the Schoenfeld center of certain fusion categories, right? But there can be multiple distinct fusion categories whose Schoenfeld centers are the same UMTC. So you can regard that as I said, the internal charges of an anyon, okay, are gauge degrees of freedom. So you can regard these distinct fusion categories. They define different gauge choices of defining the internal charges of the corresponding anyon in the UMTC. Okay, So to fully capture this gauge invariant, it is highly understandable that the charges in the original model may be enlarged to cope with the gauge transformation. So this is enlarged. And this A acts on different copies of the same object in the algebra distinctly. Okay. So go back to this example. I'm done soon. So go back to this Fibonacci case, which has two simple bimodules. Okay. The tail degrees of freedom, the set is enlarged from the original 1 and tau to 1, tau 1, and tau 2. Okay. And the original tau is embedded in the enlarged space of tau 1 and tau 2 as a linear combination of tau 1 and tau 2. And this can be obtained by requiring that the new degree of freedom in the dual model are orthogonal. So we can obtain this embedding of the old charge into this new set of charges, which are basically gauging just a different gauge. And now, if we go back to the previous example of condensing the fluxon, pure fluxon in the Fibonacci case, you see we can condense a pure fluxon m tau bar. These are trivial modules, so they're trivial. So this is truly a creation operator of pure fluxon m tau bar in the dual model. And we knew that how this is stamped, right? We knew that how this is stamped. And if we take we perform the duality map, going back to the original model, this pure fluxon creation operator or ribbon operator turns out to be a linear combination of all these four distinct dion creation operators. And the projector is a sum of the identity operator and this non-trivial fluxon creation operator with a particular coefficient. And this projector is mapped by the duality map to be the projector in this original model in which we condense the diodes of puzzle bar. So it is a superposition of all these possible dion creation operators. But which diodes are truly and how they are truly condensed? This is the question. To answer the question, we have to diagonalize this projector to see which are the truly diodes that are condensed. So after the diagonal, you see here in the dual model, we knew that the condensed pure fluxon is m tau and tau bar. M tau plays the role of tau in the original model, right? So this is a very simple fluxon. Okay. So after diagonalizing this projector, we can see that the condensed guys are what? Are a combination of this pure fluxon in the original model and the style in the original model with some non-trivial coefficients. So it is this combination that plays the role of the condensate. Okay. Instead of, in this case, we simply just condense the fluxon, nothing else. This can be understood in this picture. Okay. In the dual model, in the original model, where we condense the pure fluxon of the tunnel bar, we simply, what the projector does is simply project out this non-trivial gauge degree freedom tau. Okay, so what's left is this trivial degree freedom 1. So this is what the projector does. However, after this duality map, if you want to condense the tunnel bar diode, what happens is the projector does not really project into the trivial degree freedom. It kind of projects both tau and the trivial degree freedom into certain non-trivial vector in this two-dimensional space. And this vector tells you it is in fact this combination of fluxon and diode that is condensed. And this is the only possible physical, what happens physically in this particular gauge. Okay. And in this case, the remaining degree of freedom, although it is fixed, it is a non-trivial degree of freedom, because it is a combination of 1 and tau, in this way, in this way. So it is not a full subcategory of the original Fibonacci category, but certain subcategory, because the simple object is not a simple object in the original Fibonacci fusion category. Okay. So the construction we have in this paper, in fact, it tells us a finer categorical framework than the original framework of anyon condensation using the language of unitary modular tensor category. Okay. So we have this is F is the what? Is the input fusion category of the original parent model. And this is the input fusion category of the equivalent of dual model. Okay. And we choose a full subcategory in this equivalent input fusion category, which is this S prime. So this is an injection inclusion map. Okay. And by a pseudo-natural transformation that is represented by the duality map we just constructed, this guy is mapped back to the original input fusion category. And this full subcategory is mapped to a subcategory of this F. And this is not necessarily a full subcategory. And it tells us what diodes are actually condensed. But in certain cases, they may still describe, they may still be a full subcategory, and still describe fluxon condensation. That's possible. Okay. Yeah, this is what I have told you. By diagonalizing this projector, you can figure out what are the truly condensed diode sectors and how they are combined. And we can prove, let me just go quickly through this. We can prove that the center of this subcategory S, okay, gives us the CSFA, or the commutative separable Frobenius algebra in the UMTC that describes the condensed anyons in the UMTC language of anyon condensation. And in general, it is very difficult to compute the center of a subcategory. But we, in fact, offer a physical way using string net model to compute the center. Yeah, this is end of my talk. Sorry for went too long.
Okay, thank you. Any further questions?
Yeah, this is just a big one.
Question about duality. Is there any map that we can just derive from this duality? You report the duality between topological bases when they have cosmol bases remain unchanged. So this duality is just some map that is permitted for any.
That's a good question. It depends.
Yeah.
It depends. So we are in fact in the original fusion category. We take a Frobenius algebra, right?
Yeah.
And compute this bimodule category.
Yeah.
Right? So it happens that in certain cases that the original fusion category and the bimodule categories are isomorphic directly. Yeah. And sometimes they are not isomorphic. For example, you can go from vec S3 or vec G to rec G. And these two are in general not isomorphic fusion categories. Right? For example, vec S3 and which has 6 simple objects, but rec S3 has 3 simple objects. So these two guys, although they are dual to each other, okay, they are not isomorphic to each other. Okay. So in the case of isomorphic fusion categories, this duality map can be promoted to be a symmetry transformation between the topological orders and the underlying string net models. Okay, string net models. Okay. And this symmetry map has 2 different possibilities. In certain cases, it is a global symmetry map, which can commute anyons. Okay, so that answers your question. And in certain other cases, it is kind of gauge transformation. It does not commute anyons at all. It only transforms the internal spaces of non-abelian anyons. Certain non-abelian anyons are non-trivial. But we know that internal spaces are unphysical anyway. Okay, before you globalize the symmetry. Okay, so it can be regarded as gauge transformation. But in certain other cases, it is a global symmetry that may commute anyons.
Any other questions?
May I ask a question?
Oh, there's a question.
Through here?
Let me turn up the volume.
Oh, gosh.
Okay, yeah.
Yeah.
I would like to ask you to clarify something, okay? You have mentioned after anyon condensation, you will get a child,
Right.
right?
Right.
Okay, then my question is whether the child category can be used as an input category to describe the full category, I mean the full subcategory that describe the result of anyon condensation?
So after condensation, the remaining degrees of freedom, the remaining values of the degree of freedom on the edges in the child phase are in general a subcategory of the parent input fusion category. Okay, and the center of this remaining input fusion category of the child phase as a subcategory of the parent input fusion category. The center of this guy, okay, is in fact the Frobenius algebra in the output data or the output UMTC of the model.
Okay. So that's always the case.
Yes, yes. It
so
is the algebra that
could I see actually this is
yes, that's always.
theorem,
Yeah, that's always the case.
always a theorem.
Yes.
Okay. Thank you. Yeah, I think this is very interesting. Yeah.
Thank you. Okay, any other questions? Yes, most of us.
Okay, if not, let's thank you again. Thank you.
Thank you.